Hello, everyone. All right, can you see my screen? The slides on thin films? Yeah, okay. I'll connect my other device. Let's see how many people we have. 6 students. All right, one thing I want to mention while we wait for more people to show up, the department is supposed to select students for some scholarships. And one of them is the Boeing Scholarship, for which thus far we have received very few applications. But I am told by Dr. Morales that if you email him an application essay by tomorrow morning, it might still be possible to receive consideration. I can't promise that. He's checking on some things, but it looks like it's at least possible. He'll see if we can do some consideration. So if you were to write a page-long essay on what your career goals and interests are, and if they're relevant to something at the Boeing Corporation, then you might still be able to receive consideration. I'm waiting to hear from Dr. Morales, but all I know is that it can't hurt to send him an application essay by tomorrow. Any questions on that?
Is there a minimum GPA requirement? There is, right?
Probably, but I forget what it is off the top of my head. There were announcements sent out to students earlier, so you could go through your deleted emails or something and find that, and it will say what the GPA requirement is.
And if you don't meet that GPA requirement, I think it's a 3.2. Is it worth applying for, or do you think it just won't be accepted?
My suspicion is that we probably won't be able to accept it because the scholarship is funded by an outside donor, and outside donors get to set the rules for the use of their money. So we can't usually bend the rules that someone else put on the money.
Okay.
All right, how many people do we have at this point? Okay, we got 2 more. Let's go ahead and get started. So for the next few classes, we're going to be talking about thin films. Now, you've seen thin film phenomena before, things like soap bubbles or oil slicks. And the basic idea is that you have some thin layer of material or liquid or whatever on top of some other material or liquid. And some of the light bounces off of the first surface, and some of the light bounces off the second surface. And the interference between those 2 paths is what determines whether or not you see constructive or destructive interference. You see constructive interference if these 2 paths, if the waves that travel along these 2 paths come out in sync. So they differ by a full cycle of oscillation, or 2 full cycles, or 3 full cycles, or whatever. And you see destructive interference if they differ by a half cycle or 1.5 cycles, and so forth. And the fact that what type of interference you see depends on the number of cycles of oscillation, helps explain why these things exhibit colors. Because the distance, the actual physical distance, is the same in any case, but a distance for one wavelength, that distance might be 1.5 cycles, and for another wavelength, that distance might be 2 full cycles. Now, we can do more things with these than just produce beautiful colors. We can also produce anti-reflection coatings. And so here you see a comparison between some glass that that doesn't have an anti-reflection coating. You see glare, and glass that does have an anti-reflection coating. You don't see glare. And this is actually important in lenses, because so far, every time we've modeled a lens, we've just assumed that the light hits the interface, changes direction, keeps going, hits the next interface, changes direction. But every time light hits a glass surface, in fact, some of it reflects. You know this because you see glare, and it's particularly noticeable at night if you look out the window. Well, some of that light could bounce back and forth inside the lens. And when it does, it produces halos or lens flare. Now, if you're J.J. Abrams, you want lens flare, but most people don't want lens flare. And here's a dramatic illustration of the difference between lens flare and no lens flare. Any questions on the idea? Well, the other thing I should mention is that if you actually look at the reflectance spectrum, it's just a graph of what percentage of the light gets reflected off of a coating at different wavelengths. The reflectance spectra can be quite complicated. What we're going to do today is mostly try to understand why a spectrum has, say, a minimum here and a peak there, by figuring out how we can relate the position of the minimum or the position of the peak to the wavelength of the light and the type of materials that it's made out of. And we're mostly going to, when doing hand calculations, just talk about a single coating. The next class, we'll start talking about some ideas that involve multiple coatings. But when we're not doing hand calculations, we'll be using a Python program, which I will start explaining later today. And with that Python program, we can calculate the entire reflectance or transmittance spectrum. And so we can see exactly what percentage is reflected at a given angle or at a given wavelength. Here's a plot of reflectance versus angle of incidence. And so we'll continue with those ideas on Thursday. And then in the second half of class on Thursday, we'll have a guy who graduated a few years ago come and talk about his work at a company that makes these things. And then next week, I'll get more into the theory and talk about how you would actually set up the kinds of matrices that are used to do the detailed calculations on a large scale. I can't teach you in one lecture everything you need to know about, but I can show you enough so that you could learn more as needed and basically give you a sense of how this program that we're going to be using actually works, what actually goes into this. One thing I should say is that thin film calculations are just easy enough, just barely on the edge of easy enough that if you need to, you can write the program. I would never write Zmax. Automated ray tracing with all of those different features is hard. Thin films are just easy enough that you can write it. And to my knowledge, there isn't one standard thin film solver out there like there is for lenses, where, okay, even with lenses, there isn't one standard. There's a couple, but still Zemax is a very big name. Thin film solvers, to my knowledge, many more people have many more programs, and I couldn't find one that had a cheap educational license and also had such name recognition that was worth committing to it. So I wrote my own. Consequently, it doesn't have a nice user interface, but all you're going to have to do in here is edit a few lines from here, where it says, hopefully, start of section that you can edit, down to here. Everything after this should be left alone. And the inevitable question I'll get is, does that mean we should not edit anything after this line? Yes, that means you should not edit anything after that line. But let's start by talking about how thin films work so that we can at least start to say, oh, well, if we've got something with this thickness and these materials, then here's where the peak should probably be. And then we can check it with the program. Oops, didn't want to turn on the camera. Okay, let's try sharing the screen. On to lecture notes. All right, so the basic idea of all thin film programs, all thin film problems, I should say, is we have at least 3 media. N1, N2, and N3 are their refractive indices. Medium 1 is infinite, so it goes out as far as you want on the left. It could be air. Medium 2 is finite. It has a thickness D. And then medium 3 is very, very thick. Like it could be a piece of glass, and you might say, well, a piece of glass is that thick. I mean, it's got a finite thickness. Well, you know, even a centimeter is still thousands upon thousands of wavelengths of light. And so even a centimeter is many thousands of wavelengths. That's effectively infinite. So that's how we're going to treat this, that this is infinitely thick. And we've got some sort of incident ray of light. And some of it reflects right here, and some of it goes in and reflects there and makes a round trip. And then these 2 waves will add up. And you might say, well, no, wait, that's not everything, because some of this wave that made a round trip, well, some of it bounced off there, then it could bounce there and go through. Yes, we could get even more reflections. But it turns out that if you do the more precise calculations, all you really need to know, at least for a single layer, for multiple layers, all bets are off. But for a single layer, you can get almost everything that you need to know just by considering these 2 paths. And if you only think of those 2 paths, you'll actually get pretty accurate predictions. You won't get all of the quantitative details correct, but you'll get a lot of them, and you'll certainly get the positions of the peaks and the minima. So if you're looking at it and trying to say, okay, well, now we've got a graph of reflectance versus wavelength, and it's got these peaks here. Why are there troughs there, and peaks there, and there? Well, you could do a calculation with just these 2 paths and figure it out. And those of you who have taken Physics 2530 probably already saw that. We're going to review it again anyway today, and then go into greater depth with software and go into more elaborate situations, and then talk about, finally next week, the theory behind going many layers farther out. Any questions so far? So the idea is pretty simple. If I call this my first reflection, and I call this my round trip, if both of the waves look like this, just adding two waves like that, we get constructive interference. They're at the same point in their cycle. Wherever one of them has a peak, the other one has a peak. Wherever one of them has a trough, the other one has a trough. Conversely, if one of them looks like this, and the other one looks like this, then we get destructive interference. And these are a half cycle off, because where one of them has a peak, the other one has a trough, and vice versa. All right, pretty simple. You could just say, all right, well, how much extra distance did this cover? And so we could say that we get constructive interference if 2D, which is our round trip, equals lambda, 2 lambda, 3 lambda, etc. Or they'll often just say m lambda, where m is an integer. There's a complication. If the distance traveled is a wavelength or two wavelengths or whatever, then yes, they'll interfere constructively. But what's the wavelength? What wavelength should we be using?
What's the application again?
Could be anything, but we need to know the wavelength in this material. So it should really be lambda over N2. Right? We always want to talk about this in terms of the wavelength in the coding, which is lambda naught over N2. Lambda naught being the vacuum wavelength, over the index of the coding. Now people will say, well, let me give you an example. I mean, a very common situation is air, magnesium fluoride, glass. It will turn out, for reasons we're going to get to in hopefully later this class, otherwise certainly next time, that it's desirable to have a material whose refractive index is halfway between air and glass. But it's actually very difficult to find a material whose index is halfway between air and glass. The theory of thin films is not hard. If you took a graduate level optics class on the theory of thin films, you would know just about everything you could possibly need to know from an optics perspective on how to design these. As it is, you already know a lot about how to design these optically by the end of 3 lectures. And with one graduate class, you know pretty much everything. And yes, there's always some fine details, some new application, especially things with some of the more exotic materials coming along. But if we leave aside some of the more exotic materials out there, all of the theory that you need to know can be learned quite easily. That's not the hard part of this. The hard part of making thin films, the reason why people make a lot of money making thin films, or at least can make a lot of money, is not that the optics is hard, but that somebody says, okay, I want a material that has this refractive index, and I want to attach it to this other material, and I needed to make a nice smooth layer. It has to attach uniformly with a nice uniform thickness. And when it attaches, I want it to form a nice solid coating. I don't want it to be more porous than we expected or less porous than we expected, because if it had more pores or fewer pores, then there might be more air or less air, and that will change the refractive index. I want to know its refractive index, and I want to know that it will attach, and I want to know that it will stay attached. And if we put it in water or heat it up or do whatever, I need to know that the coating will stay on there and it won't crack. And it's all of those difficult things of know that it attaches, know that it's smooth, know that it won't crack under these conditions. Those are the really hard parts of this. And so ideally you would have, for an anti-reflection coating, and we'll get to anti-reflection in a bit, for an anti-reflection coating, ideally you'd have an index of about 1.25, not quite that, but close to that. Almost exactly halfway between air and glass. But you don't just get to say to the chemists and material scientists, all right, I'd like to get an order of 1.25 refractive index, please. You know, it's not a deli counter where you go up and say, yeah, just give me a slab of 1.25 index. Yeah, and yeah, I'll take a half pound of that salmon while I'm at it. It's not like that. You have to get something that will attach. And among the robust materials that can attach, one of the first things that people learned about was magnesium fluoride. All right, well, there's a second complication. It turns out that the first reflection and the round trip, they don't just differ in the number of cycles of oscillation because, you know, one of them went a longer distance, so it's behind by however many cycles. We also have what are called reflection phase shifts. I feel like I'm leaving something off. Well, we'll deal with that later. We also got reflection phase shifts. So, N1, N2, N3. You know our waves coming in. Looks like that. The first reflection is often turned upside down. All right. If N2 is greater than N1, the reflection is flipped, meaning that the wave came in like this. It touched the surface, let's say at the top of its cycle. It gets reflected at the bottom of its cycle. More generally, if reflecting off a higher index material, the reflected wave flips. And flipping a wave is like adding an extra half cycle. Now you might say, are we adding an extra half cycle or subtracting? And the answer is yes. And I know that's a flip, sarcastic answer, but that's because for a wave, for a sinusoidal wave, going ahead a half cycle is the same as going back a half cycle. They have the same physical effect. So, all right, this first reflection might be, depends on the indices, depends on what N1 is. There's no guarantee N1 is 1. It could be that we're talking about light in starting off in glass. For instance, if we've got a lens, we've got a coating, then here N1 equals 1, N2 equals whatever, N3 equals probably about 1.5. And we'd figure out, okay, what do we have to do to minimize reflections off of this surface? But then, when it goes through, all right, now starts off in 1.5, N2 equals whatever, N3 might be 1, or it might be water, 1.33, whatever. So what I'm trying to get across to you is don't always assume that N1 must be 1, okay? We could easily have a problem where the light starts off in air, goes into whatever, starts off in glass, goes into whatever material, winds up in air. Any questions so far?
For so I know you mentioned that for like when we go from N1 to N2, where N2 is greater, you'd have a reflected wave. For other indices, is it ever, I mean, I know theoretically we sometimes consider a wave to be partially transmitted and partially reflected.
Oh,
I mean,
just about every surface has partial transmittance and partial reflectance.
right. In a real life case, that's always the case, right?
Well, for transparent materials, yeah. And strictly speaking, even things that we call non-transparent, there's some tiny penetration depth, but we won't worry about that right now. So go on with your question.
Oh, I guess I just wanted to clarify that fact, I guess, and how, if we need to account for it.
So what's happening is that whatever makes it in is certainly a weaker wave than what hit the first surface. It has a smaller amplitude than the wave that hit the first surface. That is certainly true. Because some of it got reflected here and the rest got transmitted. So this is a weaker wave. Now, once this wave hits N3, again, it could be reflected at the same point in its cycle if N3 is low index, or it could be reflected a half cycle off if N3 is higher index. So let's just consider the case for now that N1 is 1, N2 is 1.38, and N3 is 1.5. And let's just work through what would happen. Let's talk about our first reflectance. Do we get a phase shift? Yes or no? Don't overthink it.
Yes.
Yep. Okay. Our second reflectance is also phase shifted. There's a 1/2 cycle due to the interface here, due to the fact that N3 is 1.5, it's a high index. N2 is 1.38, it's a low index. And then there's a round trip, 2D over lambda over N2. So the distance divided by the wavelength is the number of cycles, or 1/2 plus 2N2D over lambda. Now let's say we want anti-reflection. Then the difference what should the difference between these be equal to? Do we want, how many cycles should the difference be if we want anti-reflection?
half a cycle, right?
Yeah, because we want this first reflection to cancel out this round trip. So wherever this round trip is in its cycle, we want this thing to be half cycle off from that. So we want 1/2 or 3/2 or 5/2, etc. So we want, I'm going to write this as m plus 1/2, where m is an integer. So 2n2d over lambda equals, because these halves here canceled, m plus 1/2. And so we will get reflections if d is equal to m plus 1/2 lambda over 2n2. Any questions on the steps leading up to that? Let's say m equals 0. We'll consider other cases later, and you'll see why m equals 0 is an important case. It won't be obvious when we do m equals 0, but it'll become more obvious after we do m equals 1 and 2 and 3. So m equals 0. So then the thickness should be 1/2 lambda over 2n2, or lambda over 4n2. So this is often just called a quarter wave coding. You might say, well, it's not 1/4 of the wavelength, because you'd have that n2. Well, that's 1/4 of the wavelength. Lambda over n2 is the wavelength in that material. So 1/4 of lambda over n2 is 1/4 of the wavelength in that material. Now, what if somebody says, okay, well, that's great, but I don't want anti-reflection. I'm trying to achieve an effect. I'm making a toy or packaging, and I'd like to have a bright, shiny reflectance. So I want constructive interference. Now, what should we do? Set up the problem for anti-reflection up here. What should we do differently?
Well, for constructive interference,
Yeah.
it's different.
Yes,
Sorry.
it's different. Okay, different problem. We do something different. What is different?
The phase shift.
What?
Is it? Sorry, I can't talk well. It's I'm sorry, I'm brain farting.
Well, instead of the difference being a half cycle or 1.5 cycles, it should probably just be a full cycle so that both waves wind up at the same point.
That's what I meant to say. I'm sorry.
So D equals m lambda over 2n2. Well, some people will say, okay, well, what if instead of being given a wavelength and having to work out the thickness, we're given the thickness and we want to know what wavelength will be strongly reflected? Well, then we just go with the same thing here and we just solve for lambda. So we would say lambda equals 2n2d over m plus 1/2. And lambda equals 2n2d over m. Same thought process works either way. If somebody tells you, I need to have an anti-reflection effect at this wavelength, you figure out what thickness will give you the desired result. If somebody says, hey, here's this coating. We made something with this thickness. What wavelength will give you constructive or destructive interference? Well, you just use this approach.
And that lambda is the wavelength in the material?
No, that would be the wavelength in vacuum. Lambda over N2 would be the wavelength in the material, and that would be D over M.
Got it.
And let's run with that idea for a little bit. If lambda over N2, the wavelength in the coating, is D over M, then you basically get constructive interference in cases like this. You get constructive interference. No, it should be 2D over M, sorry. So you get constructive interference if your wave, if we could fit a half cycle in there, and you're thinking, why a half cycle? Lambda is 2D over M. Well, lambda in this case, this would be M equals 1, lambda equals 2D. If lambda is twice the thickness, then half the cycle fits in here, and the other half the cycle runs outside by the same distance. Or this, M equals 2, or this, M equals 3. It looks conceptually a little bit like the particle in the box in quantum mechanics, for those of you who have taken 2540. There are some key physical differences. It's not a particle in a box. It's actually the opposite. Well, no, actually there is some confinement. There is some notion of confinement. We'd have to do more with writing. We'd have to do a lot more to make the analogy a strong one and talk about the time it spends bouncing back and forth. But there are, the key difference, of course, is that there's light passing through. But, you know, it should remind you of particle in the box problems in quantum mechanics. Any questions? Anyone? Anyone? Bueller? Bueller? All right, then. Another case. Air, and 1 equals 1. N2 equals 1.45. This is vegetable oil. N3 equals 1.33. So little oil slick in your kitchen. You spill a little bit of vegetable oil into some water. And what we want to know is, let's say that D is fixed. You have to figure out what wavelengths would give strong reflectance. So I want you to try for a few minutes on your own. And actually, not even on your own, I'll put you into some breakout rooms and try it. And you'll have to think about the reflectances. You'll have to think about the refractive index difference at each interface. And let's see what you come up with.
So when we have constructive, I think we set that to equals m, right?
Right.
Yeah. And then we could solve for lambda like that. I'm guessing. Yeah.
It would just be 2n2d over m.
So what's the phase shift of the round trip wave?
Wait. This one? Right.
Yeah.
This one. Isn't it 1/2 plus this one?
Where'd the 1/2 come from?
Because it's being reflected.
Off of a
back.
higher index medium?
Oh, it's not. Okay. That
All right,
makes
try again.
sense. Okay.
Gotcha.
So what?
Well, low transmittance should apply generally to many wavelengths. But what we're trying to solve is for what wavelengths would be constructively interfering by passing through this thin film.
Yeah.
So I guess the ones that would get amplified more than the others.
Dr. Small, could you clarify the question? I think we're
Yeah, strong reflectance, so constructive interference.
oh, okay.
And would you be solving, I guess this is where I get confused, is since we're solving for which wavelengths show strong reflectance, would you solve for the wavelength or would you solve for lambda over n, which would technically be the wavelength of that material?
Well, if you have the information needed to find lambda in vacuum, you have the information needed to find lambda over n. So same thing. Normally, we always refer, when in doubt, lambda means lambda naught, wavelength in vacuum.
Okay.
That's what your instrument would read out. But if it has a wavelength of 600 in vacuum, it's going to have some other wavelength in vegetable oil and yet another wavelength in water, whatever.
Okay.
You're a very quiet group. You're a gas of non-interacting fermions, each in your own energy level. Let me double check my notes. Let me see the chat comment. 2n2d over m minus 1/2. Yeah, that looks good to me. I think I'm going to close down the breakout rooms now.
Professor, I think you're muted.
Yeah.
Oh, sorry. Do we get a reflection phase shift for the first wave?
Yeah.
Yeah, because we're reflecting off of a higher index. But over here, this one, do we get a reflection phase shift there?
We do not.
No, because we're reflecting off of lower index. You might say, well, it's not lower than air. No, it's not, but it's lower than the index of the medium that the wave was in right before it hit the water. And that's what matters. So what we're going to have is that one of these phase shifts will be 2d over lambda over n2. And the other will be 1/2. If we want strong reflectance, then we have to set that equal to an integer. And so we are going to get the 2dn2 over lambda equals m plus 1/2, which looks a lot like a condition that we had earlier for destructive interference or anti-reflection. And then a question you could ask is, wait, is that a condition for destructive or constructive? And the answer is yes. And the real answer is it depends. All right, a condition that might give you destructive interference in one situation where we go from low to medium to, I'll do it up there, when we go from low index to medium index to high index, could be a condition for the opposite when we go from low to high to medium. And so we wind up getting that lambda, why is my pen not working? Lambda equals 2n2d over m plus 1/2. Now, some people got something different. Some people got lambda equals 2n2d over m minus 1/2. And you would get that if we took the difference the other way. If we said 1/2 minus 2d over lambda over n2 equals m. Actually, that wouldn't even, that would give us then 1/2 minus m equals 2d over lambda over n2. So we could get 1/2 minus m, or we could, I'm not sure, how did you get m minus 1/2? You didn't do anything wrong, believe it or not. You just did something that requires careful interpretation.
So for the first reflection, I put that it was 1/2. And then for the second reflection, it was just the 2n2d over lambda.
Mhm.
And then added them should be equal to an integer.
Oh, but it's not the sum. I mean, it turns out to be right.
Mhm.
It does turn out to be right because calling that first, here's a valid way to do it. The whole idea of it, the idea of adding is wrong because it's the difference between the two waves.
Okay, so they should be subtracted.
Yeah, you have to subtract in order to figure out the phase difference, to figure out how much further ahead is one wave relative to another. But here's why that's actually not, why you nonetheless got something that could be valid. It's something that a lot of textbooks try to gloss over by always adopting a certain convention. And like in 2530, I would just gloss over it, but let's confront it head on here. There's no difference between a phase shift of a half cycle forward and a phase shift of a half cycle backwards, right? With a sinusoidal wave, I'll just draw a sinusoidal wave. Pick any random point, let's say here. So it's not a peak or a trough or anything that's uniquely, that's particularly special, right? Here's a half cycle difference. If we go ahead a half cycle, well, we would just go, I won't do it like that. We would just go a half cycle. We would see that it is there. Here's another half cycle back. We would see that it is there. So whether I go to the right a half cycle or to the left a half cycle, I wind up looking at the same point. Now you might say, well, it's not literally the same point on this sine wave, because one of them is here and the other one's there. Yeah, but look at them. They're both just a little bit to the right of a peak, because we started off a little bit to the left of a trough. We go a half cycle and we're a little bit to the right of a peak. So a half cycle phase shift is one of those things that you can do forward or backward, and it has the exact same effect. So for convenience, I've been writing 1/2 for that phase shift. But I could have just as easily said that this first wave gets a -1/2 cycle phase shift. And this still gets 2d over lambda over n2. So I could do 2d over lambda over n2 minus -1/2 equals m. 2d n2 over lambda plus 1/2 equals m. 2d n2 over lambda equals m minus 1/2. I get the same result as you got earlier by adding. Adding is conceptually wrong, but it happens to give the same result as doing something that is correct but unusual. And at this point, someone could say, so which is it? Which is the right answer? And I say all of them. And you say, well, how can these two possibly both be the right answer? And I maintain that they absolutely are the right answer, as long as we're very careful with one more assumption. Anyone care to guess what we have to assume carefully?
Which, like one for the top one and the bottom one, they both use different m values. I mean, offset by 1.
In the top one, we could totally have m equals 0. M equals 0 would be a perfectly valid number to put in there. Because if we plug in m equals 0, we will get 2n2d over 1/2 or 4n2d. If we plug in m equals 1, we will get 2n2d over 3/2 or 4n2d over 3. Or we could plug in m equals 2. We would get 2n2d over 5/2 equals 4n2d over 5. All of those are allowed. We plugged in m equals 0, 1, 2, and we got these 3 predictions. Down here, m equals 1, well, I get lambda equals 2n2d over 1/2 or 4n2d. M equals 2, I get lambda equals 2n2d over, let's see here, 2 minus 1/2 is 3/2 or 4n2d over 3. Plug in m equals 3. That is 2n2d over 5/2 or 4n2d over 5, and so forth. So I get all of the same actual numerical predictions. If we wanted to, in the end, get out a number and then compare that number with the number that would show up on a spectrometer, like the kind that we're using in the 2540 lab, if you've taken that class already, we'll get the same numbers out. We get out formulas that look different, but in this formula, m equals 0 is a totally allowable thing. In the second formula, m equals 0 is a nonsensical thing. It would give us a negative wavelength, which is not really a prediction we can make much sense of. Any questions on that? This problem involving numerical conventions is that perfectly straightforward that everybody understands it completely and has no questions whatsoever for me? Okay, we'll pretend. So we've got a formula for constructive interference. For destructive, the difference would be 2n2d over lambda minus a half equals m plus a half. So 2n2d over lambda equals m plus 1. Or lambda equals 2n2d over m plus 1. Now, m equals 0, totally legit this time. M equals minus 1, not so much. M equals 2, M equals 1, totally legit. M equals 3, M equals 4, whatever. Any questions on how I got to that? One thing you should notice is that for either of these formulas, as I look at the position of the first and second and third and fourth peak or trough, m is in the denominator. So everything is getting smaller. Everything is tending towards 0. So if everything's tending towards 0, the positions of those peaks are getting closer together. Peaks give you peaks correspond to constructive interference. The positions of the troughs are getting closer and closer together. So if I were to make a plot of reflectance versus wavelength, it would look like that. The peaks would start off far apart and then get closer and closer. The troughs would start off far apart and then get closer and closer. All right. And we're going to verify that on the software before the end of today. But I want to give you another way of looking at these things. All of these conditions we keep getting. In all of the cases, that 2n2d over lambda equals m or m plus a half. And sometimes that's a condition for constructive interference. Sometimes it's a condition for destructive interference. But either way, we keep getting things of that form. Now, let's see, I'm going to write that as 2d over lambda over n2. So 2d over lambda over n2 equals m or m plus a half. Can you think of any quantity that has a wavelength in the denominator, some basic property of a wave? Something we talked about a few weeks ago when we were talking about the formulas for waves, something that had the wavelength in the denominator.
Frequency?
Spatial frequency.
Spatial frequency.
K is 2 pi over lambda over n, or the length of the K vector, okay? So we've got something that looks almost like that, except that instead of having a 2 pi, we have a 2d. Well, let's just multiply both sides by pi. So we get 2 pi over lambda over n2 times d equals m pi or m pi plus pi over 2. Now, whenever we work with waves, you should remember that in those formulas for waves, we kept getting k multiplied by a coordinate again and again in wave calculations. And we also tend to, in all those formulas for waves, we tend to have interesting things happen when something is pi or pi over 2 or 2 pi, because we're dealing with trig functions, and trig functions wind up either being +1, -1, or 0 when the input is either an integer multiple of pi or pi over 2. And we're not going to see the full details of this until later, but since we were doing this, I wanted you to take note of that pattern. Any questions? All right, let's take a 10-minute break. And when we come back from the break, go into Blackboard. And if you haven't already done so, download the Python program that I posted with today's materials. Should be under files used during class on April 20th. And there should be multi-layer films posted version .py. Download that and open it in your favorite Python interpreter. And we'll come back in 10 minutes. All right. So let's go back to the anti-reflection coding. Simple anti-reflection coding on glass. And 1 is 1, and 2 is 1.38, and 3 is about 1.5-ish. Thickness D, first incident, first reflectance, round trip. First reflectance gets a 1/2 cycle phase shift. I'm writing it as +1/2. You can write it as -1/2, doesn't really matter much. Even if you wrote the second, well, we'll just do the second reflection or round trip. I'm going to write it as 1/2 plus 2n2d over lambda. And so their difference is 2n2d over lambda plus 1/2 minus 1/2. And in order to get destructive interference, m plus 1/2. Now, these are canceling out to 0. But if I had turned one of these 1/2s, if I had flipped the sign of one of these, so let's say I had 1/2 minus 1/2, which is 1/2 plus 1/2. Well, then we'd have 1. And now 1 doesn't really change anything for all the reasons we just talked about. All right? We'd have to be a little bit more careful. We'd have a 1 over here. And we would subtract it from the other side. And so we would get m minus 1/2 in all of our calculations. Wouldn't really matter too much. All right, so with that aside out of the way, again, we get that D is equal to m plus 1/2 times lambda over 2n2. And let's say if m equals 0, D is lambda over 4n2. If m equals 1, D is 3 lambda over 4n2. All right, well, let's pick this one. Okay, let's say D equals 3 lambda over 4n. Actually, let's not even do that. Let's just ask where the peaks and troughs are then. We're going to get anti-reflection. Let's ask where we get constructive interference. We get constructive interference if 2n2d over lambda equals m. So lambda equals 2n2d over m. We're dealing with a graph that looks like this because the peaks are getting closer together and the troughs are getting closer together. If we design it so that our first dip, so that the visible wavelength we're interested in is there, then you have to go a pretty long ways away to get to a peak. We know these things don't work perfectly. Something that gives you destructive interference at the wavelength we designed for is going to eventually give you some strong reflectance at some other wavelength. But if you design it for this wavelength, well, you're going to have to change the wavelength a lot before you see any effects there and there. But what if we designed for this wavelength? You wouldn't have to change the wavelength by nearly as much in order to see a strong reflectance. So you tell me, if we're trying to minimize the reflectance over as many wavelengths as possible, which of these wavelengths would you like to design for? This one or this one?
For the larger wavelength.
Yep, that's what I'd like to design for. And so that is why we always use the smallest film. Okay, we always make it lambda equals D over 4, sorry, D equals lambda over 4 N2. All right, we always want to work with the first destructive interference, not the second or third or fourth. I'm going over the shape of that because now I want to switch to the Python program. All right, does anybody still need time to get the program open? All right, seeing no responses, hearing no responses. So this program, you don't have to know how to write Python code. You just have to know what to mess with and what not to mess with. Everything up here is just some initial commands that have to be done in order for everything to work. And you have to import some values early on. Import some functions early on. I've defined a couple of material functions. And what I mean by a material function is I've defined a couple of functions that will take a wavelength as an input and give you the refractive index as an output. Because for real materials, as you might remember from looking at those curves in Zmax, the refractive index is not the same at all wavelengths. It varies a little bit. And for a couple of materials, tantalum pentoxide and silicon dioxide, because they're common, not the only things, but common in thin film fabrication, I wrote some functions that will return approximate refractive indices as a function of wavelength. The nice thing is you don't need to know any details of those functions. You just have to type SiO2 or Ta2O5. And sadly, a question that I get from time to time is why is the I lowercase in SiO2? And that's because Si is the chemical symbol, S with an uppercase S and a lowercase I is the chemical symbol for silicon. Okay, so here's the stuff that you can edit. There's a bunch of true or false values: plot transmittance, plot reflectance, plot absorption, plot field. True or false, you decide which one. It'll just determine what kind of output you get. Then you have to tell it what output, what mode you want it to work in. Meaning, do we want to fix the angle of incidence and vary the wavelength in evenly spaced steps? By angle of incidence, I just mean the direction the wave is coming in at. In that case, you might say, well, let's do 400 to 700 nanometers, 50 wavelengths. And so, okay, I got to cover a range of 300 nanometers. We'll go every 6 nanometers. We got to cover 50. We got to cover 300 nanometers with 50 calculations every 6 nanometers. Or, not that you're going to use this much, but you could fix the angle of incidence and compute with a user-defined set of wavelengths. Maybe you don't want them evenly spaced. You've got your own thing. It'll do that. You could fix the angle of incidence and vary K, vary 2 pi over lambda in even steps. We won't use it much, but it's convenient for testing certain ideas. Fix the angle of incidence, compute with a user-defined set of K values. Here's a more common one that we'll use. Fix the wavelength, vary the angle of incidence in evenly spaced steps. We'll use that quite a bit. So all you ever have to do is you just have to decide which of those modes do I want to work in. It's usually 0 or 4. And then you just set mode equals 0 or mode equals 4, whatever. Let's all set mode equals 0. And then I've got it set up to work with 1,000 wavelengths from 0.4 to 0.7 microns. I don't know, 1,000 is kind of, well, that's fine. It'll run pretty fast. Any questions so far? We also have to decide what angle we want coming in. Let's say initially 0 degrees. So just put a 0 there. And I multiply it by pi over 180 because we have to convert from degrees to radians. Python, like most mathematical software, prefers radians over degrees. So all you ever have to do is just type in however many degrees, and as long as you multiply by pi over 180, the conversion's done. You may be thinking, well, do I need to change anything for these other modes? Nope, because all of these other things here just have a statement else, elif, which just means else if the mode is 1, we'll then do these things. Else if the mode is 2, do those things. These we're not going to have to mess with much, but if you were to ask it to plot the field at a particular angle and wavelength, it'll do that. Now we get down to the things that we actually have to change for specifying the materials. We've got a left medium index, which is N1 in the way we've been doing things in class, and a right medium index, which is N3. And you might be thinking, well, why don't we just call them N1 and N3? Well, N1 we could get away with, but N3 I would rather not use, because if we have many, many layers, our third layer might not be the thing on the right, okay? Might not be the thing on the far right. I want a variable that always refers to the thing on the far right. Then there's one more thing you need to specify, a list called coding layers. And let's just start with the absolute simplest case possible. The first one, all right? Test case, actually, this one. It's one other thing about Python you need to know. In Python, a pound sign means comment, something that's commented out. The person reads it, the computer ignores it. Let's uncomment test case 1. You see how it says test case 1 here, calibrated to give reflectance maximum at 0.55 microns for 30-degree incidence if the left medium index and right medium index are 1.0. So all we do is uncomment that. We don't change any of the numbers in here. We just uncomment that. And then we make sure to change these to 1.0. And we go up to mode 0. And we change the angle of incidence to 30 degrees. Then we have to make sure all of the other test cases are commented out. Let's run it and just see what happens. And you're thinking, well, nothing happened. Well, that's because we have to look at this. Test case 1. All right. I said in the comments, the test case 1 is calibrated to give a reflectance maximum at a wavelength of 0.55 microns. And when I look, indeed, both of these plots seem to have a reflectance maximum at 0.55 microns. So it did what we said it would do. Any questions? Somebody must have a question.
How did you bring up the graph again once you run it?
I just went, it should be down here. It might be over here under plots if you're using Spider. If you're using Spider, it's either going to be under plots or it's going to be down here. Now, there's something, whenever you run Spider for the first time, there's some event, there's some command you have to put in so that it will not, so that it will display plots as separate windows. Because if it displays them as separate windows, then it's easier to zoom in. It's much harder to zoom in if they're not displayed as separate windows, but we can, this is why Stack Exchange exists. We'll look for that later. Other questions? What message is it? Figures now render in the plots pane by default to make them appear inline in the console. In the plots pane by default. Okay, so Benjamin, when it says that, what's happening? Are you getting them as a separate window or are you getting them somewhere up here?
I'm getting them up there in the plots area.
All right. To mute inline plotting. So plots pane options menu. Oh, Christ. It's probably there. Go click on that. Mute inline plotting. Anybody else? Did that fix it, Ben?
Should I try running it again then?
Yeah, try running it again. They should show up as a separate window.
So what's the box right underneath the plots area?
It's right here, these three little lines.
No, I know, but like where the tabs, there's a one big tab on the left. What's the one on the bottom right?
Here?
No.
I think it's showing up in the console.
Yeah,
area.
the console area.
Yeah.
Oh, Christ. Yeah, there's some, you know what, we'll deal.
Yeah, I can look at it on Google or something.
Yeah. Does anybody else have questions? Besides that issue, which we'll deal with on Stack Exchange after class. I can think of an obvious question. Why is it showing reflectance TE and TM? What are these two different reflectances? Does anybody know? So a few weeks ago, when I introduced electromagnetic waves, I said that you've got the direction of the wave, the K vector, and then the E field has to be perpendicular to the K vector, and so does the B field, and they're perpendicular to each other. But the E field could be in any direction. If my finger is the K vector, well, this is an allowable direction for the electric field. This is. Any direction that I might orient my pen, I could swivel my pen around my finger and it's still perpendicular to my finger. So we can break a wave into two types of waves. We could say it's a combination of something where the E field is like this. This is one direction perpendicular to my finger. And this, which is coming out of the screen now, which is another direction. And when we have something hitting a surface, this page of notes is, say, whatever surface it's hitting. If it's TE, then when the wave hits the surface, the electric field will be in the plane of the paper. This would be much easier to explain if we were in person. I have some three-dimensional models for it. But think of the electric field as oscillating in and out of the screen and hitting the paper and oscillating like this. That's TE. Okay. TM is just the opposite. The electric field is like this now, and the magnetic field is like this. So for a TE wave, the electric field is going into the screen, and the magnetic field, which will be the black pen instead of the red, Jesse Christology, this will be so much easier in person. Guys, get vaccinated so that we can do classes in person in fall. The black pen would be the magnetic field. For a TM wave, you switch them. Now, for normal incidents, there's no difference, because for normal incidents, they would both be hitting the page head on. The electric field would be in the plane of the paper, the magnetic field would be in the plane of the paper. And if I rotated it, guess what? They're still in the plane of the paper. As soon as you go off axis, all hell breaks loose. And we'll get to that in the next few classes. So let's go in here and have them just hit at normal incidence. So what things would I change to have them hit at normal incidence? Just theta naught. It's the only thing that I would change. So I just go, we're working in mode 0 where we're applying everything versus wavelength for fixed angle. And I just changed theta naught to 0 degrees. And let's comment out the test case, because I don't want to edit my test case. All right, I never want to edit my test case. Let's just go up to here, create the variable coding layers ourselves. And you have to have double brackets. And the reason why you have to have double brackets is that you've got a pair of square brackets that are going to hold all the layers. And then each individual layer is within its own pair of square brackets. So we're going to have a layer whose thickness, for each layer, we specify the thickness. And let's say that its thickness is, well, it's going to be lambda over 4n2. Let's design for 532 nanometers, a nice bright green. So lambda will be 532. By the way, don't ever type the word lambda in Python. Lambda means something else entirely in Python. It'll screw up your program. We're going to make it a quarter of that. So I multiply by 0.25, and I'm going to divide it by 1.38. And then that's the layer thickness. You might think, well, why don't I just type in a number? Well, because I can't do 0.532 times 0.25 divided by 1.38 in my head. So I just think of it as, okay, I'm going to design for this nice bright green laser pointer, 532 nanometers. I have to divide by 4 or multiply by 0.25 and divide by my code, my layer index, which is 1.38. And then I put in my layer index. And I want to put this on SiO2. I'm going to close all of these others. Close all of these. And sure enough, I get something that has a reflectance that drops pretty sharply around 532. And you may or may not have this magnifying glass tool to zoom in, but if you do, you can zoom in and we can verify that the dip is awfully close to 532. It's not exactly there, but it is pretty close. Any questions?
Professor, did you change anything for the right medium index?
Yeah, I replaced it with SiO2. If you don't replace it with SiO2, you get something that's very messed up.
Oh, okay, I see. Mine was already in SiO2, so okay.
If you do it the other way, we get, if we flip it, if we just change one of those phase shifts, we get a peak there. Instead of a trough. All I have to do is change one phase shift and we can turn a peak into a trough or vice versa. Other questions?
Yeah, it's saying my SiO2 is undefined.
It's saying that SiO2 is undefined.
Yeah.
Share your screen. I'll turn off my screen share.
So.
All right, let me magnify.
I think he put 0 instead of O.
Oh, gosh.
Computers can't do that. Oh, you know what I mean. Now, does it work? Yeah.
Yep.
Okay.
Thank you.
No problem. All right. Let me get back to my screen share then. Let's do something else. Let's try to understand now. We said that we could do lambda over 4 or 3 lambda over 4. Let's do 3 lambda over 4. So instead of 0.25, let's do 0.75 and just rerun it. By the way, this thing here, this thing that keeps coming up, this is a plot of the field profile. So this is start at the bottom. It makes more sense to start at the bottom instead of the top. Here's a graph of refractive index versus position. It's 1 in the air. It's 1.38 in the coating. The coating thickness is out to about 0.3 microns, give or take. And then it's 1.4 something, almost 1.5 in the glass. And here's a graph of what the field looks like in there. If you're annoyed with having that pop up all the time, then plot field, change it from true to false. Well, let's look at 0.75. When we look at 0.75, when we change that coating thickness to 0.75, you notice how the dip got a whole lot narrower? That's not good at all. To see what's going on, let's look at a wider range of wavelengths. Let's go from 0.2 to about 1.4. Point 0.2, we run into a problem because all of these things were approximate. So let's go from 0.3 to about 1.4. Oh, we gotta go out further than 1.4. What you should see is here is a narrow dip. Here's what looks like part of a wide dip. Let's go out to like 3. Here's a wide dip. Here's a narrow dip. I'd always rather work with the wide dip rather than the narrow dip. So what I need to do is basically bring that wide dip to shorter wavelengths because everything's proportional to the layer thickness. The wavelength at which we get either constructive or destructive interference is always proportional to the layer thickness. So let's bring that in a little bit by just scaling it down. Let's go back from 0.75 to 0.25. Let's use the thinner layer. And then let's examine it over a wide range of wavelengths. And you see just how wide that dip really is. Somebody must have a question. Well, let's change a few things. Need to just check something. Okay. Let's go with some different layers. Let's make this simple. Let's make this 1.5. I want some things to be exact. And let's make this coating layer, the square root, this refractive index, the square root of 1.5. We can just literally type square root of 1.5. All right. Let's run. And if you make that intermediate layer thickness, the square root of 1.5, it sure looks like the reflectance goes to 0 there. And if I zoom in more, it continues to look like it goes to 0. And now you might see it's a little bit choppy because remember, we told it to only work at a specific set of wavelengths. And we've zoomed in so fine that we can actually, we're actually noticing that we didn't just tell it to do an infinite number of wavelengths. But it sure looks like it goes to 0 there. Well, that's kind of interesting. Any questions so far? I'm setting up a mystery that we'll deal with next time. Let's make this even more interesting. Let's make this water. And let's make this the square root of 1.33 times 1.5. So we're going to do 0.1 of lambda divided by the square root of that index. And that index is going to be the square root of the product of the other two. Okay, what do you know? Again, we get, oops, pretty much almost exactly to 0. Any questions? All right, before next class, spend some time practicing with the software, work on a practice assignment. They'll just walk you through some basic thin film calculations. Next time, we're going to try to make sense of this mystery and then go into what happens when you work at other angles. And then we'll have an alum come and talk about working with thin films in the private sector. Have a good day.